Thank you. It's very nice to be here again. Today, and this is because I chose the CommSec track to submit today, I will show you something that is a little bit older, but nevertheless interesting because the story of this was never told before. So what I'm talking about is the original elevator, the history of private iOS jailbreak. And yeah, who am I? I'm Stefan, I'm from Germany. I do information security for nearly 20 years. And yes, I'm this PHP security guy that somehow made it to iOS. And yeah, I was running for 9 years a company in Germany called Section 1, which does mostly web and application auditing. And then I concentrated more on something called Antidote, which is a similar company. And last month, I started here in Singapore, like a branch office of this company. So if anybody of you is looking for a job, you maybe can hit me up later. Okay, so what is it that I'm talking about? This is this elevator. So what is the elevator? So back in 2011, there was a lot of hype in the jailbreak community, and especially I was involved in that because I had recently released at this time a jailbreak or a part of a jailbreak, and all these people were now basically reading every single word of mine and trying to understand how all my words have something to do with jailbreaks. And basically back then I had this complaint that in our house the landlord was always disabling the elevator every time someone would move in or out. So basically I just posted this on Twitter. And unfortunately, a few jokers, like named by Matthew Switch and the Grug, they thought it's funny to just like comment about this and say, oh, this is actually like the code name for a private jailbreak called the elevator. And it only took like minutes, like half an hour or so, and suddenly all these jailbreak news sites that were trying to get clicks, they were like announcing this new next iPad jailbreak called the elevator. And yeah, this got more and more hyped up, and it was impossible to stop this hype. I sent a few tweets saying this has nothing to do with the jailbreak, but of course people don't read that. And they only read the things that have to do with jailbreaks. So at this point, me, Matthew Switch, and the Grug and some others, we just went along with it and made a lot of fun out of it. So from this time, I would like start to tweet, and this here, for example, is so freaking good news. The elevator is working again, and it's not raining inside. So, which basically said my elevator is no longer broken, I can use it, and there's no rain inside. But the thing is, when you were mentioning the word rain back then, everybody was thinking of jailbreaks because all the jailbreaks had names like Black Rain and whatever rain. And anyway, so I was always giving these harmless tweets, and people always thought this is like the announcement for the next jailbreak. And until today, I'm getting, cussed out for that. Okay, so back then, elevator was really just like my elevator. And, but the whole story about this basically made me think, and I was like, okay, from now on, every of my private internal jailbreaks will now be called elevator. So since then, basically, I really have an elevator jailbreak, and it's basically always the code name for my private one. And this talk here is about the very first one of these private jailbreaks. Back then it was for iOS 5. Okay, so when we talk about jailbreaks, there's usually like a very important part, the kernel vulnerability. So let's first look at what the kernel vulnerability was. The vulnerability is in some system call that is called set attribute list. And this system call allows you to specify the attributes of a file, including like the file modification time, the create time. So a lot of things that are theoretically very harmless, And that's why the system call, at least back then and maybe still today, is allowed in most of the sandboxes. So even in a very sandboxed case, you were able to trigger this system call on a subset of files, but we didn't care, we just needed any file. So if we can execute the system call against any file, we can trigger the vulnerability. Yeah, as you can see, there are a number of parameters that you have to give to the system call when you call it. And the first, of course, is the path name of the file that you want to modify. Then you have to give it something that's called an attribute list. And this attribute list is basically just a collection of bit masks that tells the system call, so which attributes do we actually want to set? So it's basically a number of bit fields. The next thing then is a user-supplied attribute buffer. And we also give it the buffer size and some options. But basically, this attribute buffer contains all the data for all the attributes that we want to set, and only for the attributes that we want to set. So of course, when this system call runs, the first thing it usually does, it verifies its parameters. And then the next thing it does, it basically uses this attribute buffer from userland and copies into kernel buffer. It does that so that it doesn't have to copy the buffer part by part. So it takes the whole buffer, checks if the size does not exceed 8 kilobytes. And if it's smaller than 8 kilobytes, it will allocate this on the kernel heap with a function called malloc. And then the next thing it does, it basically copies the user data, all the user-supplied attributes into kernel land. So that's the beginning. Then the parsing starts. And the parsing of this buffer happens in the way that first the cursor is set to the buffer start. And later on, during the whole parsing, the cursor always points to the current position in the buffer. Additionally, it also keeps a pointer to the end, so it can check if you go over the bounds. Then it basically checks for every bit in the bit field, for all the possible attributes that you can set. It will check, do we have the data for that, or don't we set this attribute? So the moment we have this data, it basically then takes the data out of the buffer and applies it to some internal data structures. So it usually uses a number of macros for that. They're all called attribute unpack, and then whatever data type they unpack. So this is done for all these smaller attributes like timestamps, UIDs, and all this kind of stuff. But sometimes there are bigger attribute data sets that need to be registered with the kernel. And in these cases, instead of having the data directly at this position in the buffer, what they put there is called an attribute reference structure. This attribute reference structure is basically just two values, a relative position inside the buffer from this current position where the actual real data is, and then a length for that data. So long attributes are not stored in the sequence of the attribute data. They are basically usually stored towards the end of the buffer. Okay, and this is very important because the bug involves this structure here. So this here is the vulnerable code. And this is basically the code that passes out of the buffer whenever you try to set a volume name. Because this function can also be used, the system call can also be used to not only set file attributes, but also volume attributes. So here, this is the code to change the volume name. And the first thing that happens is it sets the volume name pointer to the current cursor, which means it's the current address in the buffer. The next thing it does, it unpacks this attribute reference from this address. And now it works with this unpacked attribute reference. So the next thing it does, it basically adjusts the volume name with the offset from the attribute reference. So it adds this to the volume name. So keep in mind, this is an integer, a signed integer, so it can be positive or negative. The next thing is, it then checks that the volume name was not just put outside of the buffer with this adding the offset. And it also checks that if we have the volume name plus the length, that we are still inside the buffer. And finally, Apple decided that all these volume names need to be zero terminated, and they ensure that the data is zero terminated, so they write a 0 byte at the end of that volume name, so usually inside the buffer that is supplied by the user. However, this whole thing has a problem. I mentioned it earlier. This data offset inside the attribute reference is a signed integer. So when you add it to the vol name pointer, you can actually make it point way outside of the buffer in front of the buffer. And then the write later on will happen outside of the buffer because this check in the middle will not check against the start of the buffer, it will only check against the end of the buffer. So if we have moved our volume name outside of the buffer in front of it, this check will never trigger. So we write outside of the buffer in front of it. So to make it more visualized here, this is what will happen. We have this allocated. By the way, whenever we allocate something with malloc, there is a size field in the beginning. And then we have the volume name pointer is the yellow box. And now we add the attribute offset, and suddenly we are in this red area, and we add the length to it, which might be 1, and then we have +1 minus 1 is 0, so we write exactly at this position a 0 byte, which is outside of the buffer. So it's a heap corruption outside of the buffer. It's a single 0 byte write. So then this was found in iOS 5. I wrote the exploit for it and used it for my private jailbreak. And then suddenly iOS 6 came out, and this was fixed, theoretically. So Apple tried to fix this, which basically means the Apple developers were kind of aware that there was a security problem or some problem, and they started to fix it with iOS 6. But as so often, they didn't get it right. And they actually didn't get it right for 3 years. One reason for that is likely, or maybe, I don't know how they work internally, but it could be that some developer just saw a crash report. He saw what maybe the reason is, he fixed it, and it was never escalated to the security team to highlight that they just had fixed a security problem. So maybe this was just a developer like fixing the code at this point and made it not crash anymore. So the fix that they applied was basically they added this new security check in there where they check that the data offset that we're giving to the code is not below 0. So the idea is now the volume name plus the address will always, plus the delta will always be inside the buffer because it's always positive. So then the security check afterward will catch when we go over the end and everything is fine. So that was the basic idea. Well, I rewrote my exploit and it still worked. So why? Because this is not the only problem in this code. So then a year later, iOS 7 came out, and we could see in the source code that Apple had applied another fix. This time the fix they applied was they are checking that the attribute length is not 0. So you can see down there, they write to the volume name at attribute length -1. And if you have a 0 in the attribute length, you would write to volume name offset -1, which would be 1 byte in front of the volume name. So in the case of iOS and macOS, this would likely not be exploitable because this byte directly before the buffer would be in the size field of the buffer, and the highest byte of the size field on a little endian system would always be 0 anyway. So we write a 0 over a 0, so that would not be exploitable normally. On a big endian system, this would actually be exploitable. So if you had like a very, very old Mac with PowerPC, then you would still have an exploit. So, but I just told you that I just rewrote my exploit and continue working. So that was not the actual problem I was talking about. So there must be more problems in this code. And this here is basically the problem that remained all the time and that Apple didn't see it. The problem is when we add this data offset to the volume name, the data offset cannot be 0, but it can be a very, very, very high positive value. And on a 32-bit system, and back then, at iOS 7 time, there were nearly only 32-bit systems. So on 32-bit systems, this can wrap the pointer around the address space. So suddenly the pointer is smaller than the buffer. So it will check, will pass the next check for sure. And then, because we also control the attribute lengths, we can basically address every single byte between the beginning of the address space up to the buffer. Because the first addition will just wrap the pointer around to the low half of the address space, and then the attribute lengths can move it around up to the buffer. This means we can still write anywhere in front of the buffer a single 0 byte. So with iOS 9, Apple finally rewrote the whole checks, and as you can see, they have now written a lot of security checks here, which is basically parameter verification overkill. They have a number of checks in there that I believe are redundant, but still they do this. Likely they do it so in this crazy way because modern C compilers have this habit to try to catch edge situations that are impossible, and then they optimize some of these checks away. Okay, so this is the vulnerability that the jailbreak used. We can write 1 0 byte outside of the buffer before the buffer, and Apple didn't get it patched between iOS 6 and 9. So how do we exploit such a thing? First of all, the lifetime of this bug was from early versions of iOS up to iOS 8.4.1, the last one before iOS 9. I personally knew about this bug since iOS 5. Between this time, there has been lots and lots of changes in iOS. And because of the different changes in iOS, I had to write different exploits for the same bug just because of the changes of the architecture of iOS. So let's look at iOS 5 first. So back at the time of iOS 5, there were no mitigations in kernel land. So writing a kernel exploit on iOS 5 was, how Tajeman calls it, a walk in the park. There was also no userland dereference protection in iOS, so the kernel could directly use userland data structures. And even worse, there was no protection against userland code being executed in the context of the kernel. So back then, all the jailbreaks basically tried the following. They would map some malicious data and malicious code in userland, and then they were using the memory corruptions to change kernel pointers into userland pointers. So for example, by decreasing the 8.0 often enough to be in userland address space. This is, for example, a famous bug by CommSec, who were able to trigger a decrement repeatedly. So you would take a pointer in the system call table and just decrement it as often until it was basically pointing into userland. In our case, we can write a single 0 byte. So this means we can easily make an 8.0 something pointer into a 0.0, which is a userland pointer. And because we can also directly execute code in userland memory, but in kernel context, there was no problem to get code execution. So the way how this would work is the first step would be we need to do some heap feng shui. And what we would do is we would fill the kernel heap with C++ objects by opening a driver connection to this Apple JPEG driver usually. with this API function iOS service open extended. And this function would also allow us to give it XML properties, and these XML properties would then be passed into C++ objects in kernel land. How this actually works in detail, there's a whole talk about this from Black Hat 2012, where I introduced this OS unserialized XML heap feng-shui technique. So if you're interested in that, just go back to that talk and look at it. But basically the trick back then was you can first of all create all these objects, and then you can poke hole in the middle of these objects by putting the same key into a dictionary again that was previously used, which would then trigger a free of the previously put object. So in this case, you can see it in the graphics. We have first created a bunch of objects with vtables, and then we have poked a hole in the middle of them. So that is the heap feng-shui. This is the setup. The next thing now is we need to trigger the memory corruption. So we call set attribute list and give it a buffer size so that the buffer will be the same size, including the size field, as one of these objects. What will happen then is that it will be loaded into the same position as the previous object, and we now have placed it in between those. Now, when we trigger the memory corruption by having like these illegal values in the attribute data offset, we can actually write a 0 byte somewhere in front of our buffer. In this case, for iOS 5, we can choose, for example, to overwrite the highest byte of the nearest vtable pointer. Previously, the vtable pointer would point to some kernel data structure of all the method tables. And now we have made it 0 in the highest byte, so it now points to userland memory. This is basically how it will look like. We have this real vtable in kernel that points to the real kernel code. And we have this object there with the overwritten 0, and suddenly it points to userland, points to our fake vtable, and this fake vtable would point to some kernel shellcode that we can just put into userland, because remember, this is iOS 5, there's no protection against this. The way you would trigger this is basically just close the driver connection, then all the objects get destructed, and including your overwritten vtable will be triggered. So iOS 5 old, not so interesting. Let's move to some modern OS. So the next OS we would be interested in is iOS 6. And this is the milestone in the world of iOS exploitation, because this is the first version of iOS that comes with kernel level mitigations. There's a bunch of them, but the most important here in this case are KSLR. So the kernel address space is randomized, mostly the kernel base address is randomized. We have no more user space dereferences, because they are now switching the page tables when you enter the kernel. And, which is even not mentioned on this here, you cannot just jump to userland code. This is also not possible, because when you run in kernel level, basically none of the userland memory is basically paged in. So even if you would jump there, there was nothing be there, so you cannot. This means we have now two troubles. The first one is we need to first break KSLR, and the second is we need a different way to trigger the execution in kernel land, because we cannot just put the code in userland. So back in this time, breaking KSLR, there were a bunch of info leaks that became public around this time. I've listed here 3 of them that were known, to my knowledge, to many parties back then, which was mach-port k-object, which was kex request. Both of them, Apple needed several times to fix them. And the last one is actually very special, because while it was known to certain parties since the time of iOS 6, it got really famous last year, because the last one, this IO registry entry get property bytes, is the kernel information leak that was used by the Pegasus iOS malware. So that one was really used in malware in the wild. But I know a lot of people who knew about this bug since the time of iOS 6. So any of these could be used to basically break KSLR, but that would be too easy for this talk. So we try to do it a different way. So the first thing what we want to do is we need to exploit this memory corruption iOS 6 to just create an info leak. So what we do is we first again have to set up our heap. And what we're trying to do is we fill the heap this time with very specific IOKit objects. This time we take OS data objects. And we do it in a way that the actual OS data object and the data storage are stored in the same memory zone, are stored basically interleaved right next to each other. So when you do that, your heap could look something like you see in the picture. You basically have the object with the vtable. It points somewhere, is a pointer to the next data storage. Then you have the next vtable, which points to the next data storage, and so on and so on and so on. The next thing would then be you need to poke the hole again. In this case, we poked the hole at the very end because it's just like hard to visualize otherwise. So we have set up our heap now. We have basically these interleaved objects, data storage, object, data storage, and then we have a hole. So if we now trigger the memory corruption, we call set attribute list again with the right parameters so that the allocation will be in the same size, and we get allocated into that same hole. I have now also visualized that there is a data pointer in each of these objects that actually points to the data storage. So I will visualize like this because when you now trigger the bug, what will happen is you can now target this data pointer with the relative right, and this time you not overwrite the upper byte, you overwrite the lower byte of the data storage. The idea is now that you make the data storage pointer go to, in its lowest bytes to 0, which means the data storage pointer now points earlier into the same page. In this case, I have like faked that. You can see the data pointer now points suddenly to the very first object in that page. This is not necessarily really the beginning of that object. It could be in the middle of an object. It could be somewhere at the in another data storage. It could be anywhere. It really depends on how big your objects are and what the alignment will do to your pointer when you just zero out the lowest byte. So you need a little bit of control over your heap when you do that. But what happens now is, in this case, our pointer just points to the beginning of an object. That means when we now use this IO registry entry get property bytes function that I mentioned earlier because it had this vulnerability, but we don't use the vulnerability, we don't exploit the vulnerability, we use the API for its usual use case to basically ask for the bytes in a property of an object. So we would then ask for the bytes for this specific object down there. I'm not sure if I can. Oh yeah. We basically ask for the property of this object, which will then follow this pointer here and give back these bytes. But as you can see, these bytes here basically contain the vtable pointer, which means we just have leaked a vtable pointer, which is the pointer inside the kernel image, which means we now know where the kernel is located. We have broken KSLR. Again, as I told you, making the lowest byte here 0 does not necessarily mean that this points to the beginning of here. It could also point maybe here, depending on where this block here is and where this block here is and where this 0 byte ends. So you could also end up with something like this here or somewhere else. Why do I say that? Because depending on your heap layout, you're not only leaking the kernel pointer, you also leak a pointer in the heap. So then you basically know the heap location and you can use that in the next run to basically put data into your kernel at a specific address. So we assume for now that this gives us the heap location and the kernel location and at the same time. If it doesn't, you would have to redo the heap feng shui and choose a little bit of different offsets, and then you have a different pointer. Okay, we assume we got both in the first run. Now we do the exploitation stage. We want to take control. So now we do heap feng shui again, but this time the heap feng shui, we do basically 2 heap feng shuis in 2 different positions. The first heap feng shui basically sets up the same kind of interleaved data storage, but this time we fill the data storage with a fake object. What is a fake object? A fake object is basically a fake vtable that we can choose because we know the heap address. We could also make it a real vtable of a different kind of object because we know where the kernel base address is. We can basically set up any kind of fake C++ object that we want. Then the other heap feng shui that we do at the same time is targeting a different size. We are now spraying the heap basically with arrays, and all of these arrays are just containing pointers to these orange objects. You can see that here we basically have an array that points to an array bucket, and this array bucket is filled with pointers to all of these different orange objects. And we create a lot of these, and this is our heap feng shui, the second one. Now we poke the hole again and we run the exploit, but this time we are not targeting these objects with our hole punching. We target these array buckets with our hole punching, and we get our malloc block inside here between all of these arrays. And this time we trigger the 0-byte override, and this time we trigger the override into one of these array buckets, and we basically zero out the lowest pointer here. Keep in mind, these pointers here are all pointers to objects. But this time we have overwritten this with a 0, so suddenly this no longer points to that object here, but it points to one of the fake objects. Which means we have now an array, and one of the entries points to an unreal object that is completely faked by the attacker. Yeah, and this basically means when the kernel touches this array now, it will touch our fake object, will trigger the vtable, will trigger whatever belongs to this object. So we can trigger basically any kind of code by having like a pivot gadget there. We could have a different kind of gadget there that gives us more control. It's basically up to what the exploiter wants. But usually you would put in pivot gadgets in here that puts the start of put the stack pointer into the heap, and then you would start a rob chain maybe from here. Okay, so this was iOS 6. Now let's fast forward to iOS 7. And you would assume that every time you do this with a new iOS version, the exploit gets harder and harder and harder. But this is actually not the case. So the exploit for iOS 6 would theoretically work on iOS 7, but Apple did a bunch of changes into iOS 7. They mostly changed things in the heap. So if you have ever heard one of my heap talks, you would know that there's something called the page list feature. So basically Apple added something new to this system where everything that uses this new feature has extra metadata in the heap, so that they can have faster garbage collection and all this kind of stuff. So it's basically a performance feature that they added, and they only use it for certain zones, so not for all allocations, mostly for the small allocations they use the new feature. Everything that's bigger they don't use the new feature for. What they also did back then when they created this new metadata, they put double linked lists in there that were completely unprotected. So if you've ever done an exploit in Windows World or anywhere else, and you exploited the heap, you would know that the first thing that people were exploiting were double linked lists. Every time you have an unlink from a double linked list, this was exploitable. So basically Apple put unprotected double linked lists everywhere over the heap of iOS 7, so that exploitation got really easy. And that's why I rewrote the exploit to see how easy it really gets. So the first thing is, I don't want to do this whole info leaking stuff that is just like not really required. We know bunch of info leaks. So why do this? We have all these bugs. So I just used the kex request info leak. Kex request was basically an API that gives you information about the loaded kernel extension and the kernel. One of this information is basically a dump, a binary dump of the Mach-O headers of the kernel and of the kernel extensions. And if you know file headers, you know that in these file headers there are usually load addresses. And these load addresses basically give away the kernel load address. So Apple would try to remove this ASLR slide from these load addresses before they give it back to the user. They failed in certain cases, and this is something that Mark Dowd and Tajimand immediately noticed when they did their talk about iOS 6.0. And they disclosed that one vulnerability. But the thing was, this function had a bunch of other bugs that were maybe related, but were not exactly the same bug that Mark Dowd and Tajimand mentioned. So this is basically was the case. So there were other ways to do it, and Apple more and more learned from public jailbreaks that there were still holes in there, and again and again and again. And it took them a while, like 2 years, to actually get all the bugs fixed. This vulnerability is also quite famous because apparently while Apple failed to fix it all the time, the CIA said thank you and were using that, and they called the exploit ironic. Because they learned about it from my talks. Anyway, so yeah, so we have this, so we skipped the whole info leak. We are only interested in doing the memory corruption. And this time, we abuse these new metadata in the heap. So what we do is, we call set attribute list. You see, we're not doing any heap feng shui. We don't need heap feng shui. We just call set attribute list, and we say the user buffer is a little bit above 1 page. This will trigger an allocation where we have this allocation a little bit longer than 1 page, and the size field will be a little bit bigger than 1 page. No heap feng shui. The next thing is we trigger this null byte write, but this time we are not triggering actually something before the buffer. We are triggering it to write to the second byte of our own size field. We make our second byte 0. So this 10 becomes 0. That means the previously very large size field is now very small. This means that when free is called on this thing here, then free wants to put this in a very, very, very small zone. And all the small zones use the new page list feature. The large one does not use the new page list feature. So what does it mean? It means when the free happens, it takes our buffer. It assumes at the end is metadata. But there is no metadata because we control all of this. So when it tries to access the metadata, it actually accesses whatever we put there. So that means we fully control this double linked list. We fully control the counter. We fully control the back pointer to the zone. What we can do now is we can manipulate the counter so that when this free happens, this free counter drops to, or is raised to the allocation size, which then means it realized, oh wait, we just freed the last used element in this page. So this means we need to remove it from our queue of partially used pages, and we need to add it to our queue of all free pages. So this means it will unlink our fake here, and when we control this, we already won. So what we do is we set up our fake metadata to the next pointer points to a scratch buffer. We are only interested in the lower byte, so we can make it anything we want the lower byte, because our scratch buffer is 256 plus 7 bytes, somewhere in kernel land. There's actually some very good places for that. This scratch buffer will be overwritten at position 4, but we don't care because it's all scratch buffer. Our previous pointer in the fake metadata will point to our target, so anywhere in kernel address space. What happens next is we have this unlink. This unlink will take the target address that we want, trash it into our scratch buffer, and then it takes the address of the stretch buffer and writes it to our target address. So we are only interested in the lowest byte, so it writes a 4-1 in the first byte here. The nice thing about this attack is we have no heap feng shui. We just have calling the system call once, a legal free that is completely survived. So we can redo this attack as many times as we want without destabilizing the heap. We can even call the garbage collection in between to get rid of what we did to the heap. And basically it means we can write anything we want anywhere in kernel land to any position. So we can create any kind of data structure and make the kernel use it. The best target for this is usually something called a kernel task port. When you have a kernel task port, you can export it to userland, and then userland can use API functions to read and write kernel land. You can allocate in kernel land, you can set memory protections with that. So basically you can load arbitrary code into kernel and execute it. So basically this is completely toasted. So this means we didn't need heap feng shui. We made the very complicated exploit very simple and very stable, like 100% stable. Yeah, unfortunately, Tajeman blogged about this problem of the unsafe unlink. So in iOS 8, Apple killed this. So the iOS 7 exploit would not work on iOS 8. But you could use the iOS 6 exploit again on iOS 8. But I would suggest to use one of the real info leaks, like for example the property bytes one, instead of trying to run the exploit several times and doing the heap feng shui so many times. It's better to just have a good info leak and then run the memory corruption only once. Yeah, so this basically is the history of this vulnerability and how it was exploited. And the conclusion here basically is that Apple sometimes is very aware of security bugs, but this still does not mean that they actually really fix them. So they declare them often fixed, but they are not really fixed. The next thing you should learn is that there are architectural changes between iOS version. Sometimes they are really dramatic, like especially when it comes to the heap. For example, the iOS 7 heap was very different from iOS 6, but also the iOS 10 heap is very different from iOS 9 when it comes to exploitation. So these changes happen, but it doesn't mean that Apple always improves everything. Sometimes they do really stupid things. So for example, the unprotected lists, so that exploitation suddenly becomes a lot easier. So I'm nearly running out of time, so you can see this topic is very, very long and complicated. So there will be more details and actual POC code released in the next week when I'm back in Germany on this website here in our blog. So all the different exploits will be in more detail be made public. Also, yeah, I said it before, we just started this branch in Singapore. So if you're interested in iOS or macOS, just contact me and we can see if we have maybe some work for you. Any question about the content, not about the job? Yes?
Do you, about the jailbreaks, do you think the lack of jailbreaks in the last years is because business matter, is because of technical, because it's becoming harder and harder to get it, or is because people is not really into jailbreaking anymore and it's not needed?
Okay, let me rephrase or make your question easier. The question was, is the lack of jailbreaks for example, iOS 10 or so, is it the reason of it becoming too hard, or are there other reasons why there are no jailbreaks? And I would say the thing is, the guys who want jailbreaks, they want normally a jailbreak that is fire and forget, and they want it to be persistent. And I would say that especially persistence on iOS has become incredibly hard. In the time of iOS 8, where we had so many jailbreaks, especially from China, I would say in the regards of persistence, they were really lucky because Apple repeatedly, like 4 or 5 times, failed to fix the bug correctly. So they were always using the same bug. But now they are run out of these bugs. Now persistence is really hard. The next thing is iOS experts have become so valuable for any kind of thing, not even like selling them to governments, but only like selling them to other researchers or so. So that giving out this old stuff for free just doesn't make sense anymore. Because like today we learned that Zerodium still pays like 1 million for a whole persistent jailbreak, and even 1.5 million if it does not require any kind of interaction. And this, yes, is selling to governments, but again, there are private companies that will just pay you for demonstrating to their management that this thing still exists. So they pay you like 50K just for demonstrating that a vulnerability exists. So giving it out for free does not make any sense anymore. And I think that is the major reason. And yeah. But of course, it also got harder, and the people are just not willing to do it for free anymore, this amount of work. Yeah, more questions. It's over.